Halo teman-teman, selamat bergabung lagi di channel saya Benak Arsitek. Welcome. For you who haven't come yet the first time, so welcome. For those who already watched my streaming before, uh, welcome again. So yeah, we're going to continue from our last session yesterday. What we already did is we start to create our own DSL, domain specific language, in Golang, because from the required application that we are creating, the requirement is that we must be able to do some kind of simple language. There is a expression to be evaluated because we want to make our application to be dynamic, and we can define checking into our testing mechanism, validation mechanism, and also to manipulate values to be used when we load a key, monitoring key from our context. For you who don't really understand what I'm talking about, just what I'm talking about, you can watch my previous video, which is start to talk about this DSL. Well, we are about done like first quarter of the feature that we are intended to develop, but obviously it cannot be finished so within our last session. So we're going to continue again, maybe for the next two episode, because this is creating DSL is not difficult. It's quite easy, but labor intensive. So lots of things need to be developed. Yeah. Let's discuss about IT a little bit. What is the news of IT? What is happening in the IT industry? So, yeah. Just look into the computer world. Some news that I can see here is a little bit interesting. IT job salaries stalled in 2020. US IT job. Jadi kelihatannya number of recruitment, IT recruitment, and also salary for IT people in US is a little bit going down. Well, this is I think it's all quite obvious because this is starting off COVID-19 issue, right? So in COVID-19, maybe a little bit at the beginning of 2020, people start to save money a lot to survive. So the recruitment is getting lower, and also maybe those who get recruited, the salary that they get is a little bit lower also. What else? Wi-Fi 6E. I don't know about that. Maybe somebody could tell me about it. What is interesting? Yeah, yesterday, Adobe Flash player. Adobe Flash in overall is yesterday has reached their life cycle, the end of life cycle. So starting from yesterday, Microsoft start to stop their distribution of Windows or anything that include Adobe Flash player. So goodbye, Adobe Flash. What else? Yeah, Microsoft previews native Edge browser for Apple M1 Max. So Microsoft now launching applications which is native to M1 Max. Safari so their Edge browser is more native now. Even even though they put it that it is already been native, but it is still behind. So behind native Chrome and Firefox, which is already been there. Quite funny actually. And then there is a plan by Google to actually prepare to stage Chrome OS into PC manufacturers, which is already PC manufacturers, which is already having all of their hardware quite outdated. Meaning, if you have any laptop or any PC which is quite old, maybe 10 years old, the technology already been obsolete, the processor is quite slow. Google is staging that they want to promote Chrome OS to be installed on those hardware, so everybody can bring live their old machine with Chrome OS with a good performance. This is what they say, because basically Chrome OS is just a Linux. I think it's a Chromium Linux, and then on top of it, it's a browser, and then the browser is become the main user interface. So you only need a power to run a browser, and then within the browser, then you can run many applications. So if you read this article, Google is actually going full force to encourage everybody start to use Chrome OS for all of their old machines, because obviously there is lots of machines which is me myself already have 3 laptops which is already outdated. So I'm eager to see if we can install Chrome OS in all of those old laptops, and then we just inherit it to my daughter or my cousins, my nephew, so they can start to enjoy their own laptop. Yeah. Now Microsoft released an Office for M1 Mac. I heard a lot about this M1 Mac. It's a processor which is the form factor is a little bit bigger compared to the Intel processor, because they want to fit in more and more transistor inside to make it even more robust and more powerful. Because we already know that the form factor of processor right now cannot be even smaller, because the gap between the power line, the electricity line between them is already too small, like I don't know, 6 nanometers, something like that. If you go below that, closer, then electricity might jump between canals, so it will not work with if you make it even more smaller. So instead of it's become smaller, it's become a bigger, because you want to add more transistor. Even though if you add a little bit, it's already millions, billions of transistor you can add. So M1 they say it is a beast, the new kind of processor right now. It's a little bit big, but the processing power is much higher. What else? Yeah. Do you feel it on Monday in the morning? Because at that morning, I heard that my daughter asking me that, hey, Dad, I cannot look into my YouTube. What happened? Internet is off or what? We have an outage? Then I say, yeah, let me see. And then I open my YouTube. Also, I cannot. Try to open Google, cannot. So Google is down at that time. Then I just see this. So actually, more than half an hour on Monday morning, Google is down. Oh, this is Monday morning US time, I think. So it's kind of Monday evening, something like that. So, right. So I hope I'm not mixed up with time zone here. Yeah, that is the news today. So actually, Google down everything. Gmail, Google Docs, Workspace, Sheets, Meet, everything's down. So it just, this news actually confirmed that. Okay. Enough talking. Anything? Maybe anybody want to talk about the news? Share. Okay. While let's start with our coding from yesterday. Let me prepare my IDE. New Windows. Okay. Yeah. If you follow from my first live stream, we are starting to create an application what we call as Simon. Simon is a new project from Hyperjump. It's a monitoring tools. The application, the solution is actually works very much like a what is it called? what is it? The robot thing, uptime robot. So it's a service can be used by anybody. Anybody can sign up, and then they can register. They can put their web server, REST server, or any server into the system, into the service, and the service will do check on them, check whether the performance is good, the latency is good, whether the request is valid, etc., etc. So yeah. Whoa. Okay. So the idea is that these monitoring tools is like what? This part is called Simon Agent. Simon Agent is an application which is we can install on many different parts of the world. We can running on AWS. We can running on Google Cloud, on Ali Cloud, anywhere, maybe on a VPS somewhere. So we can run it to make a cover as much as possible from different part of the world. So when some of our clients, that customer, let's say not like customer, who use our service, and then they want to monitor, let's say, can you monitor my website abc.com and make because most of our reader or our user is from the Middle East. I hope their latency is good from if they are accessing from the Middle East, and it's okay if they access it from the American continent. So we have lots of nodes around the world, and all of this is a Simon agent, and they make calls, they make like a ping into those server and see the latency, and then we report to our customer that yeah, your website have this performance when we access from that. And at this time from America, somehow your system seems to be down. It take latency more than 10 seconds or 20 seconds or never respond, something like that. So we can make an alert, pretty much like a uptime robot, but we make it a little bit different because it is more than just uptime robot, more functionality. So this one is the code for Simon agent. Basically, what we already did. We have this job. So a job is actually a monitoring job, right? So a monitoring job have a function, execute and validate. Execute means that execute this HTTP call. So we put it as an interface because monitoring can be, we can monitor an HTTP endpoint, could be an ICMP endpoint, a ping point endpoint. Maybe there is a TCP IP based protocol which is served by a server, so we need to do a socket call. So there is any implementation, could be HTTP, could be something else. So we have an interface called job. So one of the implementation is an HTTP check job. So we have an execute for implementation and also for validation. The execution is very simple. If you just read this code, it's very simple thing to do, simple logic. Hold on. Very simple logic. Oh, terima kasih Bapak Muhammad Nur. Wah, master. Thank you. Jadi we mixed between Indonesia and English now. The logic when we call execute, we get all the requirement for calling an endpoint, an HTTP endpoint, because when you want to call an endpoint, obviously you need, I'm keep giving you gesture, but you cannot see me. So okay. So the idea is that we have a context, and this engine will execute based on the context. The context, what is actually a context? Context is a simple map, actually a simple map of string to string. So the context is actually a string to string map behind. I don't put it directly as a map because I just want to have a full control over the getter and setter of this thing. Even though if we have a map type map, we can additionally add additional function into the map itself. But bear with me, this is my approach. So a map, a context. Sorry, a context is actually default context is actually a map string to string. So when we want to call something, when we want to instruct the engine to execute something, the parameters or information that we want the engine to call is inside the context. Every time the engine is done, making monitoring or calling to HTTP, whatever the result, the response code, the method, the response code, the header, response header, the response body, everything will be put back into the context. So, for example, like this. So, if you want to execute an HTTP check job, so we should get from the context the HTTP monitor count, for example, because an idea is like this. When we want to monitor an HTTP endpoint, for example, my client say that, can you monitor the performance of my dashboard? Okay, but before we're able to call the dashboard, we need to call the login first. So this monitor is actually consisting of two calls. Call to the login and then call to the dashboard. And then we measure the dashboard. We can also measure the login, no problem. So within this context, the HTTP monitor count means that there should be two calls. Okay? From the first calls, so we iterate if this key return 2, then we iterate from 0 to number of calls. So for the first call, we get the URL to call. So this is the call index, means that I have something actually to give you a better explanation. Hold on. Yeah, there you are. So for example, if we have a monitor count equals 2, then we can take, by these two, we iterate from 0 and 1. The 0, we take the URL, HTTP request URL equals the URL we want to call, and then the method that we want to use, and then the header, the content, if you want to put content type header, we can put it like that. And if we want to put the request body, then we do it like that. Okay? So from this information, the logic could prepare an HTTP request. So we get the URL. Okay, we put as a URL to invoke, and then we get the method to use for the invocation. We make sure that the URL exists, method that exists. If there is something wrong, maybe some parameters is not there, we just put back into the context here with a new key, meaning that 0 or HTTP response, you have an error. Yes, it's true. The reason is in the HTTP response error. The response is that URL is not provided in the context, something like that. So any error will be put back into the context. Any request information will be get from the context. Okay. Okay, we know the URL, we know the method, and then we create the request. Okay, from there, we want to capture the error message. Maybe the URL is not valid, maybe it's not a well-formed URL, so we need to see whether the URL is actually correct. If the URL correct, of course, the error will be nil. If it have something wrong, then error will not be nil. Again, if something wrong, we put back into the context. And for each of the map, yeah, we iterate through each of the HTTP request header dot. So whatever the suffix, that is actually will be the context to put inside the request. So we iterate that, we put into our request, and then we check if there is a body that we need to include. If we have a body to include, then we add. And then we create the client. Okay, we check. This is to check whether we should ignore if the SSL is valid or not, or invalid when we called the target URL. So if we just disregard the validity of the SSL. We just put that. Transport is a client config, insecure script verify true. So, and then we start the timer because we want to capture the latency. Well, not the latency actually, the what we call a response times. So we get the time, we execute the request, and then we get the duration. Okay, the duration we then put into the context spec. So HTTP response duration will containing the duration in milliseconds. Okay. Now, yeah, this is quite normal. Response body always closed if we're going to check for the body. And then, yeah, we take all the response header back into the context. So yeah, response header, we iterate, and then we put back into the response header context. So it is actually based on the context. The idea is that if we can do it something like this, so actually response will be put back into the context like this. So if the response is okay, then http.response.code is maybe 200 later on after execution, because the logic will put back information into the context. Or for example 0.http.head response dot header dot content type equals maybe application, something like that, right? So when we want to execute the second request as defined, this is coming after the execution line. Okay, when we want to make the second call to call the dashboard, we need to put authentication, which is the value is actually coming from the previous call, right? So we need to make sure that the authentication header will include bearer and then some function. That's why we need to create some kind of expression, right? This is our own language. We need to get a JSON path from the previous, this is the 0, means the previous request, response body as a JSON, and then you get the path within the JSON itself, which is the data and access. To get maybe the response body would look like something like data, and then access, and then your token, the first token, and then refresh, the refresh token, maybe something like that. So if the response body is like this and it is actually a JSON, then we can make sure that this key will be evaluated as bearer. When we get value, it will be like bearer with the following key, something like that, right? It's logical. So the endpoint in abc.com/dashboard, when they inspect into the authentication header, they can see the token which is coming from the first authentication mechanisms. So by that's why we need to create our own DSL. So that is actually the idea. The DSL is still in progress. If you want to see it from very beginning, just the video before this one live, the yesterday video, is talking about how to create your own DSL. You should visit that if you want to know how to create your own DSL using in Golang. We are using ANTLR4. ANTLR4 is a excellent tools for us to create our own DSL. ANTLR will do all the heavy lifting for our task when we want to parse things, when we want to parse string, we want to tokenize everything, cut strings, we want to identify which one is actually a number, which one is a string, which one is actually a function, what is the function name, what is the argument, what is everything. So it is actually done by ANTLR. So you should go back to visit that part, because otherwise, if I want to explain that again, then our time will not be sufficient for another 2 hours. So this is what we get so far. I already created a grammar file. In ANTLR, we have a grammar file. From this grammar file, ANTLR will generate code, Go code, to do parsing. So first, we defined a grammar file. And from this grammar file, ANTLR will generate a Golang file, a Go file. And from this Go file, it will help us parse through functions and everything. This is what we have so far. So we already defined our lexer. Yeah, lexer. And this is our parser. Okay. In our lexer, yeah, anybody, if you have any question, just don't hesitate, immediately ask. I would love to answer them. Just type in the chat. Yeah, we have a lexer here, meaning this is the token that we're going to capture from an expression. Yeah, we have fragment of letters, we have a fraction of numbers, digits, a fraction of operators, yeah, and then all other fragment. And also we have a literal, a string literal, which should be started with double quote, ended with double quote, and also have an integer literal, which is an integer value. A positive integer means that it always starts from 0 or 1 till doesn't matter how many sequence of numeric letter there. And then there could be if we want to put a real letter, a real literal means a floating point, then we can have a real literal there. And then we also have a true false definition and a function name. A function name should be an alphabetic. Yeah, should not start with number. Okay, so let's visit this again. Let's see how it works with our expression. This is just a revisit. Actually, we already discussed this, and we already see how it works. So if we have an expression something like ABC, okay, then ANTLR able to detect that this is actually an expression, and it's a constant, and this constant is a string literal. Can you see? Okay. Okay, how if I say that this is something like that? Then ANTLR, we identify it as an expression, which have a constant, and the constant is an integer literal. So just by defining this grammar. So if you want to put floating point, yeah, float literal with exponent, no problem, real literal. If we want to put minus, whoa, minus is not there. I'm very sorry. Okay, how we can put minus in our literal? We miss that. Okay, float literal is actually a symbol of minus followed a real literal. Okay, integer also have a minus. That's it. So if you put a minus, so there is a minus, say that, with a literal 3, 2, 3, 4, 5. So if we put it like this, yeah, it's a string literal. So if we have something like this, 1, 2, 3, plus 5. Oh, this is a constant, is it? Expression. Hold on a second. Oh, why suddenly it's not working? Let's try. Let's create a function. Yeah, it detects as a function. And then with argument. Why is it not working now? I'm very sorry. Hold on a second. Okay. Okay, expression will content or constant. There's no problem, right? We already test that. What are we testing? We are testing an expression. This should be a valid expression. Expression should contain constant, which is contain integer literal. Oh, do we have a minus? Okay. Let's use a fragment instead of just this. Okay, string is okay. That is strange. Oh, I am sorry. Minus is optional. Okay. Okay. 1, 2, 3 plus. See, this is an expression. Now it's okay. Okay. So if we create an expression like 1, 2, 3, 5 plus 1 tambah 1. So we can identify that this expression contains two expressions with an operator in between. The first expression is an integer literal of 1. Second integer is literal of 1 also. So we can put something like that. Or so we can see that this is the first expression. This is the second expression. Yeah, something like that. See, expression, the left-hand expression actually have two additional expression, which is combined with a plus. So this is actually 1, that one, and 3, 3, 4, 5 is actually that one, and then there is a plus in between, and then yeah, like that. There is a plus 3, 4, 5. That actually this plus is actually dividing between the two expressions. This is the first expression, this is the second expression, something like that. So we can also do something like plus. It's valid. So what we're going to do with this, we're going to do a concatenations. We translate this into a string, and then we put that, we concatenate with that one. Okay, it should work. Let's create a function. Try it with one argument. Okay, the expression can say that yeah, there is a function. This expression is a function. The function name is function. Yeah, for you can see, the function is the name is foobar, followed with an opened brace, and then there is an argument list, which is containing one expression, and it's a constant integer literal 1, 2, 3, 2, 4, and then enclosed by that. You can put like this. Okay, and even we can put another function with a string plus a number. So it's all working, right? So with this, we should create our own AST. AST is a abbreviation of abstract syntax tree. So we need to create a syntaxis tree, pretty much like this one, depicted by this graph, but it is actually formed with a real object. So what we're going to do, we need to create the object to store all of these AST. So we have, for all of these parsed token expression, for example, an expression, we create an expression structure. For the constant, we have a constant structure. All of those, okay? And then from this constant, From expression, you can see that expression can only contains a constant, a function, or a two expression which is separated by an operation by an operator. So we can see that an expression can only contain constant, function, or the left side of the expression and the right side of the expression and the operator. There is no other possibility. There is only these three possibility. Function can have a function name and an argument list. So we can see that this function can have a name and also an argument list. Okay, and so on and so forth. We just follow what is already been defined by the grammar file. So yeah, operator can have all of these strings. Plus is what? Plus is a string of containing only one character, which is plus. Minus is only character of minus. So this is all the possibility that can be contained within an operator. So operator is just a string. Okay, and then what else? Yeah, so on and so forth. String literal can only contain a string literal. Integer literal can only contains an integer, so on and so forth. So yeah, integer literal can have an integer. String can have a string value, and so on and so forth. When we talk about the integer literal, I only put it as an integer 64-bit, the 64-bit variant, because we are following what Golang do. Golang in the value reflection package, when we want to translate a value into their native type, it always given in the 64 variant, be it integer 64, unsigned integer 64, or the floating point 64. Because when you get integer, get float, get unsigned integer, it's always given in 64. So there is no reason for us to actually do value in other than 64-bit. Okay, so we have all of this asked. Now we need to create the parser. Okay, so we already have the grammar, and let ANTLR generate our parser. So yeah, we just call generate ANTLR recognizer. So all the file will be here. This is actually the file that is created by ANTLR. If you don't believe, let's delete this. Okay, this is all generated code. When we run, yeah, there you go. You get the generated code. Yeah, so ANTLR actually will create all the necessary functions and structures and everything. The lexer, the parser is done by ANTLR. We just use it straight away. Okay, let's try this parser. Okay, but before we try this parser, let me explain to you about the listener pattern. So ANTLR will generate this file. What we call is as the Simon Lang listener. This listener is obviously not to be extended by anybody. It's only to be used by ANTLR, internal for ANTLR. But ANTLR also provide a base listener. This base listener is actually implementing all the interface here. The interface here. So this is the base listener. By this base listener implies that we can override the function inside this base listener. So when ANTLR try to parse a syntax like this, okay. When ANTLR try to parse this syntax, when it first find an expression, it will call the function inside the listener. Okay, when it find a function, yeah, you can go you can parse through the tree like that, where ANTLR will call this expression. Okay, without making more confusion, let me show you. Where is our listener? Okay, this base listener. You can see The name is like enter every rule. Okay, enter expression, enter function, exit function, enter constant, exit constants, enter operator. This function will be called by ANTLR when they parse the string. Okay. Yeah, when they parse this string, for example, later on. Oh, I think we okay. When we call this when ANTLR parse this function, it will try to generate this tree. Okay, it will call start expression, and then it will call start function, and then it will call the next parse node. This is not a parse node, they will not call it. So function, it will call argument list, and then start argument list, start expression, start constant, start integer, and then exit integer, exit constants, exit expression, and then enter expression number 1, enter constant, so on. Exit, 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 and then enter, 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 and then exit, exit, so on. So it will parse through the tree pretty much like this diagram. Okay. So we can implement a logic as when ANTLR start calling this listener, we can implement a logic to construct our AST, abstract syntax tree. It's very, very difficult to actually spell that one. Yeah. So assuming when we start to parse these things, I'm thinking about to explain how the lexer works. So in parsing, in string parsing, when we're talking about compiler or interpreter, there are two types of parsing mechanisms. The first thing is the lexer. The second is the parser. Lexer, what the lexer do? Lexer will tokenize or cut down the string into tokens. Okay, it doesn't matter. It doesn't care about the sequence of the string or pattern, whatever, as long as it is matched according to the. Let me show you. According to this lexer downward, as long as it found those letters, it will tokenize it. Okay. The fragment will not become a token. Those without the fragment keyword here is become the token. So plus is a token, minus is the token. Okay. String literal is a token. All of this is a token. So if ANTLR found this sequence of character inside the string, it will emit a token. Let's see what I mean by that. Okay, let's create a test. Go file, Simon agent listener test. Okay, Simon agent listener test. Okay, we have our test. Let's create a test function. Test for lexer. Oh, right. Okay, so let's create a test. Let me peek into my cheat sheet. Okay, hold on. Test lexer. Okay, we have data. For example, the data is, let's make it similar to our test. Let's use this. Copy. Test. Like that. Okay. There is no error thing. Okay. And then we have Simon Lang new. Hold on. What we need, Alexa. There's the function that we need. Okay. Stream. Why is it not including? Which? Hold on a second. No error, obviously. This error is coming from the IDE because the IDE is not yet indexed this generated Go file somehow. So it's a little bit late. Later on, it will run. It will run eventually. So yeah. Why our why? Say Simon Lang is there. Help! Why is it not working? I know. The package is uppercase. Sad face. Okay. Let's try to run this. So when we run this, it will print out the token. See? It will find a foo bar and then an opening brace and then a 2, 3, 4 and then a comma and then so on and so forth. Okay, this is the pattern found by the Lexer, and then we emit all of those tokens. Okay, so foobar is somehow match one of the token in here. Maybe it's a function name, and then followed by an open brace. and then followed by a number. Maybe it's a integer literal, and then followed by a comma. Yeah, comma should be defined somewhere here. I think it's in the argument list. Yeah, this comma. And on and so forth. So from here, the lexer will feed the sequence of token into the parser. Then the parser can see if the sequence is belong to an operator, then it will emit the operator, start operator. If the sequence is actually following the pattern of this, then it will emit this, and so on and so forth. It will keep calling the function inside the listener. So this is our listener. We can implement that later, and then this is the test. This test show you that how the lexer is actually working. Now let's put logic in our AST, the abstract syntax layer. Okay, string, easy, there is no logic. Okay, operator, now we put operator, there is no logic. Plus is plus, minus is a minus. When we look into the grammar, the thing which is meaningful actually coming from an expression and also a function. Let's see an expression. Okay, an expression could always contain constant, function, or an expression, two expression, and followed by an operator. So let's see how we can do when we can put logic into the expression one. Let's have a function. Function. The receiver is an expression. Put expression, and then we call it evaluate. Okay. When we call evaluate, it will return an interface. Okay, so expression can only contain constant or function or this three. So if constant is not nil, then the other is always nil. If the function one is not nil, then this and all this is nil. Kind of like that. So we can easily do something like this. If constant is not nil, right, we simply return the constant evaluate. Okay, yeah, I know it's not there, so let's do it. Constant, okay, also have evaluate method. So we'll do the same. Constant can only be boolean, string, integer, or float. Okay, if constant boolean is not nil, we simply return the boolean evaluate. Oh, okay, we do this for all of our types. Okay, string, integer, float. Okay, oh, sorry. Okay, now we do the same for all of our literals, boolean literals. Okay. We return value. How easy is that? Oh, see, this is not constant, this is a Boolean literal. Yeah. Okay. Just copy this for all of our literals. Okay. Float, integer. And lastly, string. Okay, so our constant can return whatever. A boolean, a string, an integer, a float. Okay, and then we already put the constant. Expression. So if the expression contains only constant, then it simply return the constants evaluate. If expression have function which is not null, then return the function to evaluate. Okay, so we have to implement this also in the function. So right now we just return nil. This is not easy to implement. Return nil. We're going to come to this later. Expression. So the function is not yet there. Sorry, my mistake. Okay. Okay, and then lastly, we make sure that we can execute this, right? If not nil and nil. Okay, then we can do this expression. So we can get the left expression evaluate, the right expression evaluate, and then we get the operator, because the operator is only a string. See, if you can see this operator, where is operator? Operator is only a string. Okay, so how are we going to do that? Expression, what is expression? Okay, so we get the value of the left expression, left interface. Let's interface is coming from the left expression dot evaluate. The right expression, the right interface coming from right expression dot evaluate, and then the operator is equals to the dot operator dot operator, which is the string. Okay, and then let's switch. Should we switch, or this is the most cumbersome task, because we need to implement all of this operator. You can see all of this operator, when it used against any data types. Data types could be string, could be boolean, could be integer, and could be floating point, the 64 type floating point. So what we're going to do, where is our expression? Let's switch switch of operator. If it's a plus, then case here, not if, oh come on, case, it's a plus, do something. If it's a minus, do something. If for all of them, oh god. Okay, so if it's a plus, minus, divisions, multiplications, what else? Let's see our grammar. We support what? We support, yeah, plus, minus, division, multiplication, modulo, logic AND, logic OR. Let's go. Modulo, what is the modulo, and then there is a logical AND. Where is it? Logical OR. Logical OR. Yeah, something like that. I don't know. Would we also do a bitwise operation? Could be, but later in the future we can implement that. Equal sign, less than or equal, greater than or equal, not equal, right? Let's put it down there, not equal. And then what again? Let's see our grammar. Yeah, we cover all of those operator. Okay, we cover all. And then default, if the operator is something else. So what we can do, okay, for plus we need to see the left and right side, right? So let's switch again. Switch the left interface dot kind. No. How we can do that? Reflect value of left interface dot kind. Okay. Case, because there is only four possible value, which is integer, floating point, string, and boolean. So we just simply like reflect dot string. This is the first possibility, and then integer 64, floating point 64, and also boolean. Okay, and then for each of these we do another switch for the right side. Okay, for the right side could be string, integer, float, and boolean. You get the idea? How many possibility that we need to implement? So, okay, if there is a plus operator, okay, and then the left side is a string and then the right side is a string, then what we should do? We concatenate between the two, right? Simply return printf to string. Oish. Which is the left side is L interface and the right interface also a string. Done. One. Okay. Next, if we do again, if the left side is a string and then the right side is an integer, what should we do? We're going to concatenate them as such. Right, this is an integer 64. And then we do it again for all of them. Floating point, Boolean, and so on and so forth. Then we need to test this. Okay, hold on. Okay, let's repeat. Now, if the left side is an integer 64 and then we have the right side is a string, what we're going to do is that, yeah, easily we can put the first side is the integer, so we need to convert this into a string. This should be an integer 64. Okay, if the left side is an integer plus integer, if two integer is getting addition between the two, so we simply return the addition between the two, right? Yeah, something like that. Make this as an integer 64. The right side also an integer 64. We just plus them. So if the left side is 1, the right side is 2, then we get 3. And then when we try to make an addition from integer 64 to a float, what we're going to do, we translate the integer into float first, and then we concatenate, we addition them. So the return will be a float 62. This is obvious, right? Okay. So what we're going to do, we're going to translate the first one, the left side, into a float 64. Like this. How? Float 64 from that one plus float 64. Yeah. So the left side, which is an integer, we translate it into a float 64 first, and then we put an addition from the right part. I hope everybody still follow, right? This is actually not so difficult. It's just a lot thing need to be done. Okay, we're done with that. How if we add an integer 64 with a Boolean? Can we do that in an addition? Addition, of course, not support. It will not support. So we put an error. Oh, let's put an error. So just return an error. Error. Okay, no problem. Others we can easily put error afterwards. Wow, there's lots of error, right? Okay, just let's add this into all of them. Into all of them. Yeah, it will return error. This nil, no error. Constant. Yeah, return an error. It will eventually correct expression. Yeah, we are working on it. No error. Function. Going to come to this later. Integer or literal. Operator have no evaluation. Okay, so let's continue. Unused variable. Yeah. Like a good citizen of Golang, I will check the error. If error equals to nil, return nil with the error. Okay. And then, yeah, no problem. All of this have no problem. In the addition, we can add anything with a string. We can add anything to the integer except the boolean. So it means that we return nil with an error. The best practice is always using FMT error. Cannot add an integer to a boolean value. Should not use capital. Okay. And then continue from there. We do with float. So if we add a float with a string, we simply we concatenate them. Okay. We add float with an integer. So we do it pretty much like that. Which is the float. The integer here will be translated into a float first. Let's move it over. Okay, this is the left, this is the right. So lazy. Okay, and there you go. So the integer will be converted into float first. We get an integer from here, convert it into float, and then we do the subtraction. The plus. Actually, it's the same, right? Okay. We just repeat this again and again. This is actually very simple addition between two float. And then if we add a float with a boolean, the same, we cannot add float to a boolean value. Okay, done. For the minus part, for the plus part, we have to do this again and again for the minus, the division, the multiplication, the modulo, and everything. But we only do for the test purpose. Let's do only the plus one, because later on with the minus, the division, and everything, I will do it off stream, because otherwise I only torturing you guys to follow me do all of these cumbersome things. So let's do with this. Oh, the boolean part is missing. Bugger. So yeah, let's do this. When we concatenate a boolean with a string, we plus a boolean plus string, true plus some string. So we just put this a value. The first one is a boolean. Okay, second is a string. When we cannot do this, like, it's always be an error. Always been an error. You cannot add a boolean to an integer. You cannot add a boolean to a float. Cannot add between two boolean values. Okay. There you go. Other than that, we just throw unsupported. Yeah. To make it easy. Not yet implemented. Okay. Let's try to test this expression. New Go file expression dot underscore test. Oh my god, test. Okay, then function test expression evaluate. Make it more specific. Addition. Okay, so what we're going to do, we create an expression, one expression. We're going to test addition, right? So what we're going to do, we first create an expression, the left side, left expression equals to an expression which is contain a constant which is contain an integer. Okay, an integer of 1 to 3, right? Constant integer or integer literal. Oh my god. Where is our test? Okay, this one. An integer literal which is the value is 1, 2, 3. Okay. And then the right side of the expression is 3, 2, 1. Okay, and then the main expression is an expression which is have the left expression and then the right expression and then an operator, which is an operator. The operator is plus. Okay, then let's see. Main expression dot evaluate should return an interface and an error. If there is an error, return t dot error, the error. Oh, not return, sorry, my mistake, there is no return. Okay, if there is an error. If not, we have to make sure that this evaluate will return. If we add integer to an integer, it should return integer, right? So reflect value of interface dot kind equals. So if the kind reflect integer, not, then there's an error. Return type is not an integer. Okay, and then we get the value. Value equals to interface Oish. How? Like that. If val is not equals to what? 444, right? Error. Value is not 444, but val. Let's try. Missing return. Ah, yeah, missing return. Return nil the error. Unknown constant value. What next? Next. Missing return at the end function. Oh yeah, this function. Okay. Return nil error. Some logic not yet implemented. Okay, let's run this. Pass. So we can see that this expression is actually working with an expression of 2 integer, right? So we need to create 2 object, 3 object, left expression, right expressions, and then we put this left and right expression and the operator, pretty much like the ANTLR preview that we did. Where is it? Okay, this. Okay, we have that 1, 2, 3 plus. See? We have an expression on the left, expression on the right, and the operator. All of these three must not nil. So you can see that within this test. Left expression, right expression. Right expression contain a constant contain an integer literal. Very similar to the test that we did. Okay. Contain an left side expression, right side expression and operator. The expression contain a constant, integer literal, and then this is the value of integer literal. So it's very much, we are actually doing it like what the graph said. Okay, so we need to create all of this abstract syntax graph in our memory and then execute them. By execute means to call the evaluate method. So we just construct all the graph just like this, and then we simply call the function in the first expression evaluate, and then it will return with the proper value. No matter how complex the function, doesn't matter. Okay. Well, that's it, guys. Thank you very much. We already done our part 2 in our ANTLR discussion. I showed you how to create the abstract syntax graph, which is actually a very simple structure where the structure is actually reflecting what is the grammar said. Expression will contain a constant or function or an expression and two expressions separated by an operator. A function should have a name, an argument list. A constant would have this and this and that. An operator should be like this, something like that. So we just imitate all of this structure within our grammar into this AST graph, abstract syntax tree node, which is argument list, boolean, literal, all of them, and then we just call the logic to actually do the evaluation. Okay, so later I will do all of this offline, off stream. So later when we talk again, we will have a complete logic on how to do addition between type, subtraction between type, multiplication between types, and so on and so forth. Okay, everybody, thank you very much. Join me again tomorrow, 2 o'clock. I stream this as regular as possible whenever I have the time for that, because I try to allocate my time starting from 2 o'clock maybe until 3:30 or maybe until 4 to do programming discussions, IT discussion, news, maybe IT gossip, anything. So see you again tomorrow. Peace. Keep safe, stay safe, keep up home, don't go anywhere. The virus is very, very dangerous, and keep healthy. Okay, thank you very much.